Hi everyone. Sorry about the lateness of this lesson. I've just had Zoom crash on me, so I'm having to start again from scratch. So please do bear with me a little bit. So today's lesson is all about thermal expansion. We've been working previously on gas laws. Now we're going to move sort of forwards onto something else, because I think you've kind of had a few weeks of gas laws and you've kind of had enough of it, maybe. I'm sorry that nobody could actually join me on this particular occasion. So I'm going to switch cameras to my desk camera. There we go. And we're going to look at the linear coefficient of expansion. Okay, so we're going to look at a particular concept today. Basic idea stems from something very, very simple. You've done some thermometry with Mr. Welsh, so you probably know some of this. Some of this will be obvious to you. Let's take a length of a particular material. It can be any solid material. It can be a bit of steel, let's say. If you take a length of material at a given temperature, it will have a length, okay? And if it's at temperature, let's say, let's call it T, if you heat it up, so T, plus a particular change in temperature, we'll have the same length, same unexpanded length, but it will have expanded a little bit. So it'll be slightly longer. It'll also be slightly wider, but we're not going to worry about that at the moment. So it will have expanded by a given amount, okay? So this would be the amount it's expanded. I'm going to call it X. You can call it delta L if you want to. In fact, I'm going to call it delta L just for fun, okay? So it stands to reason that the higher the change in temperature, the more the material will expand by. So we could say that that delta L is proportional to the change in temperature. We could assert that, and that certainly does tie in with the thermometry you've done with Mr. Welsh. Now let's imagine you've got another piece of the same material on the end of it. Exactly the same length, exactly the same width, everything's exactly the same. Okay. So it's effectively forming a piece of material that's twice the length. Now that material will expand by the same amount if it's heated by the same amount as well. So what you end up with is the same level of expansion on each half of the material. Okay. So if you've got 2L, that would correspond to an expansion of twice the change in length. So the change in length of an expanding material is proportional to its original length before it expanded, okay? So in other words, the change in length is proportional to its unexpanded length multiplied by the change in temperature, okay? Now, if that's the case, then what you have is you have this idea that the delta L is equal to some constant multiplied by the unstretched length multiplied by the change in temperature. And that constant is the linear coefficient of expansion, okay? Now, we're going to give it a symbol. I'm going to give it the symbol alpha. Why? Because you could give it any symbol. Sometimes it's referred to as mu in some questions. Sometimes it's referred to as alpha. Sometimes it's just given by a name. But we know that we can use any symbol, really, as long as we define them. So what we've got to do next with this particular constant, which is a constant for a given material. So steel has a particular linear coefficient of expansion, which might be different, say, to copper's coefficient of expansion. So what we need to do is work out what that unit is. Well, the unit's pretty simple. If we rearrange the equation, so if we rearrange this equation, well, we know that delta L is equal to alpha times the unstretched length multiplied by the change in temperature. So the coefficient would be given by the change in length, the expansion, divided by the unstretched length, divided by the change in temperature. So if that's the case, we know that's in meters. We know that is a length in meters. We know that that would be in Kelvin. You know from Mr. Welsh that the change in temperature is measured in Kelvin. So what we're looking for is meters over meters kelvins. And that implies kelvins to the -1. So the linear coefficient of expansion is in kelvins to the -1. Okay, that's the unit for it. So what does it all mean? Well, it means a lot of different things. It means that when things are heated, they expand, and we can calculate how much they expand by if we know the size of the material that's expanding, and the linear coefficient and the change in temperature. So just to give you an example now, for your task, you'll be given a different question, but I'm going to give you a question that is not on your task. Consider this a worked example. This is taken from the specimen paper. You'll have to excuse the printout. I'm running out of printer ink. I have to buy some more. So this is all about a steel-framed bridge. Now, this steel-framed bridge, being made of steel, will expand and contract with changes in temperature. So what will happen is if on a hot day, it'll be slightly longer than it is on a cold day. Now, we don't really like big structures to expand and contract, because if they're big structures, they expand and contract by large amounts, and this causes them to buckle or change shape. And you're going to see a video a little bit later all about that. Just to show you, just to sort of talk you through it and show you how we apply it is really an exam question is the best way in this case. So we've got a linear coefficient of expansion of steel is 1.2 times 10 to the power of -5 kelvins to the -1. Okay, so we now know that that is our alpha here. It says calculate the change in length of a 10-meter girder for every temperature rise of 20 Kelvin. So that is our change in temperature. So if that makes sense, we then can work out therefore the change in length. The change in length is going to be the original length, which is 10 meters, multiplied by the coefficient, multiplied by the change in theta. So if you've got a 10-meter girder, multiplied by the coefficient, multiplied by the change in temperature, which is 20. So if I was to calculate that, I've got an old-fashioned calculator here that I'm going to use. So I'd say that was 10 multiplied by, well, 1.2 times 10 to the -5. That's 1, 2, 3, 4, 5. Okay. Multiplied by 20 gives me 0.0024. Okay, or that's in meters. So that's fine as a final answer, but we're really looking at it as an example. Well, we know that that would be 2.4 millimeters. Okay, which, to give you an idea, it's about that much. So every 20 meters of that bridge would expand by that much. But remember, if you think about what a steel girder is like, it would take a lot of energy to compress it. And so if it was just restrained as opposed to being allowed to expand, there'd be a very large force involved trying to let it expand. So that would be enough force to actually buckle the bridge. It then says the bridge was built during the winter. It's expected that the temperature will rise by 30 kelvins in the summer. There are gaps placed between each girder, which is 10 meters long. Calculate the width of gaps needed to stop the bridge from expanding. In other words, to stop the bridge from sort of creating those sorts of stresses. So what we're looking for is the idea that the bridge, that each girder would expand by 2.4 millimeters. So if we look at it for 20 Kelvin, so if we were to calculate it for a change of 30, that would give us 0.0036 meters. That would be the gap you'd need between the girders in order to stop that expansion from causing the girders to push together and buckle the bridge. Okay. Now, another part of the question, another example is an accident causes a fire on the bridge. As a result, the bridge reaches a temperature 120 Kelvin hotter than when the bridge was built. The bridge is 1 kilometer long. I can just about make that out. Okay, calculate the expansion of the bridge, allowing for the gaps. So what we're thinking of here is we've got a 1 kilometer long bridge. So this would be a length of 1 kilometer, okay, which is 1,000 meters. So the bridge would expand by 1,000 multiplied by the coefficient, 1.2 times 10 to the minus 5, multiplied by the change in temperature. This time it's 120 Kelvin on average hotter, okay, which if we think about it, that's going to be a much larger number. So let's see how much the bridge would expand by if it wasn't for the gaps, first of all. Now, it's 1,000 multiplied by 1.2 times 10 to the minus 5, multiplied by 120. So it expand by 1.44 meters is the initial expansion. But we now have to subtract 99 gaps. Why 99? Because the girders are all 10 meters long. So it's 1,000 divided by 10, okay? So there's going to be 100 girders. And if you think about it, the number of gaps is going to be the number of girders minus 1. Okay, so for example, if I've got three girders, I'd have 2 gaps. So it'd be 99 times by the amount it expanded by last time, which was 0.0036. Which would be 0.364. 0.3564. So 1.44 minus 0.3564 gives us 1.08. Well, 3 significant figures would be more than enough, I think, for this question, as everything else is given to 2 or 3 significant figures. So the bridge, even with those gaps, would expand by 1.08 meters. So what would happen as a result of this expansion? Well, if the bridge is going to expand by that much, we know that stresses will build up on the bridge. Okay, and we know that as a result of those stresses, the bridge will buckle. Now, I'm going to play a short video which sort of puts that into context for you. After the video, so I'm going to show you a short video, and then after the video, try the example, and I will walk through. I'll do a walkthrough after lunch, okay? So that will be at 1:35 p.m. today. So that's what I'd like you to do. So if I switch to my video now, unfortunately, I had to reset, so it might not work. Whoops, that's the wrong one. Just going to share my screen in a moment. Bear with me, I do apologize. This is going a little bit wrong. Try again. I'm just going to go through the search just in case this video decides to not work. But I think that should work now. Okay, so I'm sharing the screen. I'd just like to watch this short video. It's going to be preceded by a couple of adverts, so I'm just going to pause recording for a brief moment.
Watch out. But I don't play games with my money. That's This video is sponsored in part by Blue Apron. More on that later.
Whether you realize it or not, you're probably already familiar with thermal expansion, which is the property of materials to change their volume depending on temperature. If you used a glass thermometer, you've even taken advantage of it. The liquid in the thermometer, usually mercury or alcohol, increases in volume as it heats up. Since we can characterize this expansion, we can put it to use as a measuring device. Maybe you've had some experience with a less useful application of thermal expansion. If you've ever put glass dishware on a burner or poured cold water on the dish that just came out of the oven, you know it doesn't go so well. If it's allowed to expand and contract evenly, stresses in the material don't build up. But if you heat or cool it unevenly, certain parts of the glass will fight against each other as they change size. Glass isn't flexible, so instead of bending, it just shatters. Thermal movement is something that has to be considered in nearly every field of engineering, because there aren't many places that don't see fluctuations in temperature. And there are really only two options for designing to account for thermal movement. The first one is to prevent movement by constraining it, a feat that is almost always impractical. Thermal movement can generate tremendous amounts of internal stress. Watch how this wire can lift up a weight just by heating it up and cooling it down. So the other way to accommodate thermal movement is just to allow your design the freedom to move as it so desires. But sometimes it's easier said than done, especially for large civil structures. This is the formula for thermal expansion. It may look complicated, but it's really not. It essentially says the change in size of anything is a linear function of temperature proportional to its length. And the slope of this line is the coefficient of thermal expansion. We've measured this property for a whole host of materials, and you can look up tables online. Lucky for civil engineers, the thermal expansion coefficients for steel and concrete are nearly identical, which is why we can combine them into the ubiquitous construction material, reinforced concrete, without worrying too much about fluctuations in temperature pulling it apart. But even though they expand and contract at the same rate, they still expand and contract. A perfect example of this is a sidewalk. Let's look back at our formula and plug in some numbers for a very typical situation. If we enter values for the average length of a city block, the average high and low temperatures in a given year, and the thermal expansion coefficient for concrete, we can see the total movement of a sidewalk over the course of a year can be upwards of 4 centimeters or 1.5 inches. Obviously, you can't leave a gap in the sidewalk that big at the end of every block, so instead, we leave small gaps spaced every so often to accommodate that movement. Most of the joints you see along a sidewalk are just to control cracking, but if you pay attention, every so often you'll see an actual break in the concrete, filled with some kind of flexible material. These are expansion joints that give the walkway the freedom to move from fluctuations in temperature. But what about structures that are longer than a city block? Thermal movement scales with length, so engineers need to take more care with linear infrastructure. Long runs of pipe, especially if they experience fluctuating temperatures, need expansion joints to prevent damage. The rails for trains can experience sun kink, where a hot day can actually buckle the steel. One of the biggest challenges for thermal movements is on bridges, so I built a little model bridge to show why. Unlike sidewalks that can have periodic expansion joints, bridges only have support between the spans. You can't have an unsupported break in the bridge, so that means all the thermal movement happens at the supports. The allowance can't be evenly distributed across the length. It happens all in one spot. For bridges with very long spans, that can be a lot of movement. I've got my bridge set up with one side pinned and the other side free to move. I'll fire up the Sunny Day simulator and watch what happens on the dial indicator. The bridge expands along its length as it heats up. This is exactly what happens in real life. Now I'll try to pin both sides of the bridge so the movement is constrained. The bridge still expands as it heats up, but now it has to expand in directions it wasn't meant to go. It's a little bit hard to show on camera, but the entire bridge has buckled side to side. I'm using flexible rod for this demo, but if a real bridge was constrained like this, the forces generated by thermal expansion would probably lead to failure of the structural members. Expansion joints on bridges not only have to allow for thermal movement while still being supported, they also have to bridge the gap in the road deck so that cars can safely drive over it. So if you look closely, you'll see lots of creative ways engineers manage thermal expansion. These are some photos collected from the web and sent in to me by viewers of different bridge bearings that allow thermal movement. My inspiration to make this video came when I was looking through some vacation photos. Take a close look at this steel catwalk over the river. The shorter cantilevered beams are welded directly to their anchor plates. They're free to move because they're only connected to the rock on one side. But look at the beams that stretch across both sides of the canyon. At first glance, it seems like they're constrained on both sides, and we know that's bad engineering. But if you look closely, you can see that they're bolted to the anchor plate using slotted holes to allow the beams to expand and contract. I hope this video gave you a little more insight into the dynamic nature of structures we normally consider static. Keep your eyes out and you'll notice allowance for thermal movement in structures everywhere you look. Thank you for watching, and let me know what you think.
Okay, so that video just really it illustrates to you exactly how important thermal expansion is. There are lots of examples of thermal expansion. One of the very extreme examples that I'm going to just quickly show you, if I just come out of this for a second, is if I look up a thing called the SR71 Blackbird. Hopefully I'll be able to show you a very, very quick image of a particular type of aeroplane. This particular type of aeroplane, oops, don't want that. This particular type of aeroplane is one that's designed to fly very high and very fast. Because it flies very fast, its outer skin heats up quite a lot due to friction, which causes the parts of the plane to expand. It expands so much that when it's on the ground, they fill it up. It's filled up with fuel, and it actually leaks when it's on the ground because it's got to have big enough gaps to allow the parts of the plane to actually expand into each other to stop it from buckling when it's at high altitudes and when it's at high speeds. So that's one particular example. As I said before, I'm not sure if that came up on your screen, but I do apologise if it didn't. As I said before, I would like you to watch make sure you've watched this video, make sure you understood it, and then I'd like to try the example that's on Show My Homework and hand that in ready for the lesson at 1:35 today, please. Okay, that's your task. I'll see you this afternoon.